We have two presenters today, Gary Spingard and Albert Tu. Gary is a product manager with Hamamatsu and focuses on detectors and light sources for the mid-infrared region. Photonic devices have been a key technology in many of his past projects as a chemical engineer. He began with the spectrometer group before moving into mid-infrared components, where he continues to support the development of gas analyzers, analytical instruments, medical devices, and pyrometers. Albert is a marketing engineer for Hamamatsu in Bridgewater, New Jersey, and he specializes in near-infrared applications and image sensors. After graduating from college, he held positions from product design, technical support, and product management in the optical industry. He has experience in product development and new technology implementation, and now uses his expertise to help customers find the right solution for their technology. And without further ado, I now pass things off to our presenters. Welcome, Albert and Gary.
Thank you, Emily. Hello, everybody. My name is Albert Tu, along with my colleague, Gary Spingard. Today, we will be talking about optical technology and industrial automation and gas analysis. Today, our topics will be mainly about different applications and also talking in a high level with several techniques. Our topic today, we'll be talking about gas analysis, semiconductor and electronics, food analysis, and some techniques that maybe will be similar to using it. So first of all, I do want to talk about why is optical detection so important. So optical detection actually nowadays with the capability of manufacturing, especially in fabrication, like solid-state devices, the noise and sensitivity compared to a couple of years ago has been extremely improved. Outside of that, due to solid-state devices nowadays are more and more common, reliability and as well is getting better and better with a longer lifetime and with maintaining the high sensitivity. Outside that, for industrial automations, specifically, sample preparation is key. Like in the past, we have to prepare samples, send to labs. And nowadays, with optical technology, non-destructive testing with little to no sample preparation and non-damaging the samples actually could help out a lot in automation or industrial inspections. Other than that, the real-time feedback, high speed, providing a quick analysis meanwhile in your process will be very, very beneficial. So in conclusion, actually, optical detection is providing it from off-site sampling. In the past, you have to just take out like one sample and then send to a lab and then come back and then confirm your quality is correct, to nowadays 100% inline inspection. For real-time feedback, you could monitor your process immediately. So that's why optical detection became more and more important, often used in automation world. So starting from this, I'll let Gary talk about gas analysis.
Perfect. Thanks so much, Albert. So as many of you may know, gas analysis is so critical to so many spaces and industries and applications. First, starting with processes from metallurgy to semiconductor, there are certain gases that correlate directly to the efficiency or performance of certain production settings. And of course, everyone is aware of the effect of greenhouse gases and environmental considerations from certain flue gas exhaust, NOx or SOx, also known as NOx and SOx, the main contributors to smog, which are heavily regulated and are an absolute must to monitor for air quality. There's even possibilities for monitoring the environmental impact from traffic in real time. And one can also not forget the need for personal safety monitors. There are so many workers out there in hazardous conditions and so many gases that present really high hazards. They need to wear personal monitors for all sorts of gases at very, very low limits of sensitivity. And I just want to touch upon real quickly a couple key areas that is wildly expanding for gas analysis, one of which is methane. Depending on who you ask, but The last factor that I heard was methane is 25 times stronger than carbon dioxide in terms of trapping heat. And there's a bit of a renaissance going on in terms of the technology in order to quantify and sense methane, prevent leaks. Leaks are not only really bad for the environment, but of course they're only bad. They're bad for business as well. Carbon dioxide remains a huge focus for greenhouse gas emissions as well. But there's also a focus for capnography, making the technology more mobile, closer to the patient, more point of care solutions. If it's possible to monitor our respiration rate with higher sensitivity, more reliability, and an instrument that could go anywhere, it could provide, it could really improve healthcare outcomes, possibly. So when first talking about gas analysis, I'd like to introduce some of the key principles, one of which is the Jablonski diagram, which kind of illustrates how molecules can interact with light. Key takeaway here is that if you have a molecule and expose it to very high energy light, say visible light, you're going to get some behavior along the lines of emission, either in fluorescence or phosphorescence. It's essentially, if you think of the classical model of weights on a spring, you're going to blow over these springs with all that energy, and you're going to get into the excited state of emission. However, with lower energy light, say infrared light, now we're in the realm of absorption, and you're changing like vibrational modes and rotational modes, and taking advantage of this phenomenon is what leads to a lot of gas analysis techniques. And we can see this manifest in certain absorption bands. This is what I like to call the usual suspects, a lot of species that are of very high interest in a number of industries. But the main point here is that if we take an example of methane, right? Exposed to 3.3 micron light is going to absorb very heavily. It's going to take that 3.3 micron light energy and absorb heavily. However, take the same molecule, say expose it to around 4 micron light, you won't get nearly as much of absorption. Now, many may be familiar, and we'll expand more upon this later, in terms of Fourier transform infrared, which is a popular technique in certain settings for gas analysis. Just a quick review, there's a broadband light source, of course, providing those all-important wavelengths for the absorption, and there's an interferometer or a Michelson system and an IR photodetector. This system generates an interferogram, and a transform of this data creates a spectra, which can provide the information for gas levels, the species, and their concentration levels. Now, Fourier transform infrared has been deployed in a number of situations, and rightfully so. It can analyze multiple species at once, provide spectral data, which can have other uses, and it's highly sensitive. The absorption principle is very consistent, and it's reliable. However, especially for the needs of today, there are a lot of trade-offs. Usually there's some sort of reference cell or cleanup step before the gas can enter the system. There is a lot of manual maintenance and even sometimes consumables. The measurement cycles can be long, on the orders of minutes to hours, and I'll touch upon this more later, but there's also process risk with hinging all of the process monitoring into a single unit. So one thing that can be done is, say, a single species analysis, and I'll quickly touch upon the principle here. So kind of similar to the Fourier transform infrared, but again, one sample here. You have the source of that light that's providing that absorption band. So let's say carbon dioxide, that source of IR light has to be providing 4.26 or 4.3. That sample is going to absorb, and it's going to absorb, how heavily it absorbs depends on the concentration. This difference in light signal will be seen by a photodetector. Also, another critical factor here is the path length, which gives the sample more opportunity to absorb the light. Typically, more path length means more sensitivity in a system. Now, there are other configurations out there and other strategies, but I'm going to touch on a couple of the main two today. One way you can create a system for a single gas species is a reflective type or non-dispersive infrared. Essentially, you have the light source and the detector, and then the gas is interacting with the light inside the chamber here, and it goes in and out. Otherwise, if there's a consistent flow, you can have a light source shoot directly across a path and then have the detector on the other side. But the principle, again, remains the same. You're relying on absorption and a photodetector seeing the difference in the light signal. Applying Beer-Lambert law, there is a linear relationship between the concentration of the gas and the difference in signal. So going to expand a little bit upon that NDIR model, non-dispersive infrared model, let's take an example of carbon dioxide. So you make one of these reflective cells, you're going to have a light source, could be LED or otherwise, but it's got to have that 4.3 micron light. But one of the critical factors here is the detector. Now, it's beneficial to have more than one detector, and I'll explain. So there's going to be a measurement channel here and a reference channel. Initially, the measurement channel is going to see a lot of signal, right? As there's no gas inside, it's sensitive to the 4.3 micron light. The signal is very high, and not so much for the reference channel. However, as gas enters this space, the carbon dioxide is going to absorb the light. Now there's less signal for the measurement channel. And how do we ultimately get that measurement? The ratio of signal between the reference channel and the measurement channel changes, and that you apply the Beer-Lambert law to that, and then you can output a relative concentration or parts per million, what have you. A reference channel is critical in a lot of spaces for spectroscopy. It provides that baseline and stability. So definitely suggest having a reference channel for instruments that are looking to resolve concentration. Over here, I just have an example of what will go inside these systems in terms of like the form factor for the LEDs, and also the possible form factor for the photodiodes or the detectors. So I'm going to kind of switch gears into perhaps a more higher end gas analysis, but first I want to touch upon a topic in terms of the near infrared versus the mid infrared. This is a discussion for a number of species, including organics and not just a single molecules. Again, taking carbon dioxide as an example, there are absorption bands in the near infrared for sure, but there's an extremely strong one in the mid infrared around 4.26. Now, when thinking about an instrument to design, now in the near infrared, the absorption's weaker, but there is a very developed line technology. It's been around longer, possibly more modules with higher levels of integration and also lower cost. The mid infrared, much higher absorption is going to lead to higher sensitivity and also less pressure on the other components to perform. However, the mid-infrared technology, I would say, is a little bit younger in the market. So one may have trouble finding solutions that are fully integrated. So it's all about a bit of a balance. There are other factors to consider, say, in terms of maybe propagation or problems with water, but be sure to discuss with your vendor if you're considering the near-infrared or mid-infrared for certain gas species. Now, when I'm talking about these absorption lines, they're very, very thin. One step to the left or one step to the right, you're having no interaction versus a full absorption of that light. But this is actually a good thing to take advantage of. And I'll explain quickly with a real world example. Let's say we are looking to analyze carbon monoxide in the open atmosphere. Now, there are all sorts of absorption bands to choose from. Seems relatively simple. Well, in the real world, there are other things in the atmosphere, like carbon dioxide, of course. I'm going to quickly add it here. Okay, create some difficulties, but you can still see some peaks here, not too much trouble. Well, water is also everywhere in the open atmosphere. So let's have a look at that. That makes things kind of get difficult. So what if there was a light source that could hit the absorption band right on the head and sort of, I want to say, dodge these sources of interference? So that will really drive up that signal and noise ratio and enable very, very, very high sensitivity. Bunch of absorption, no interference is the ideal case. And this is exactly what a lot of tunable diode laser absorption spectroscopy systems aim to do, especially with a tight band source like a DFB QCL or an interband cascade laser. Its output is extremely thin, much like those absorption bands. So since you have that output right from the get-go, you're going to get direct absorption, and you can apply that transmissive measurement, as you can see here. And contrary to systems like FTIR, there's no cleanup step necessary, none of those moving parts, that interferometer system, and no reference cell, and it can measure continuously. So that makes it very appetizing for a lot of continuous processes out there. But again, this would be for a single species. And it's exactly this principle that has enabled a lot of high sensitivity breakthroughs. Quantum cascade laser technology, interband cascade laser technology, DFB lasers in the infrared is relatively young. Specifically, quantum cascade laser technology have only been commercialized really since the early 2000s, the late 90s. The technology is very young, and there's a lot of research going on out there that's pushing the boundaries every day. And in certain academic settings, certain QCL systems have reached parts per quadrillion sensitivity. So many of you may be asking, well, why would that even be necessary? And I'm going to take a quick example. So let's consider semiconductor industry and looking for what is known as airborne molecular contaminants, usually in the form of certain acids or ammonia or HF or HCl. And one can see, and there's a whole lot of research out there that points to this, and you can even talk to a lot of fabs that over time, standards just get more and more and more tight and demand more and more purity. Why? People want to drive up yields. Less contaminants equals more yield. Everyone needs more yield these days. And in the sense, in a clean room setting, a lot of this airflow would be directed to a series of analyzers, much along the lines of that I described before, very closely monitoring for these extremely low levels of contaminants. Believe it or not, it's even a few molecules is enough to ruin some yield, and that is a no-go for a lot of semiconductor processes. And a lot of the technology we see out there today utilizes what we know as cavity ring down spectroscopy. Don't want to dive too much into this here, but the point I want to make here is like this technique has been very popular because due to this optical cavity, what it does is it effectively creates a very, very, very long optical path length. And if you remember from the main principle before, the longer the path length, the more sensitivity a system will see. So cavity ring down spectroscopy is very good at that. And I'm going to make a specific example in terms of the semiconductor industry. And I guess you can even include a FTIR in this example as well, in certain ion-based techniques, right? Mobility, chromatography, mass spectroscopy, very high sensitivity, no doubt about it. Can analyze all sorts of species. However, those cycle times are pretty long, from minutes to hours, and they can be very high maintenance. And there's a lot of calibration required, even in the sense of gas chromatograph that could consume helium. However, let's take a look at laser spectroscopy. Laser spectroscopy, the sensitivity is still very high, and that measurement cycle time is very, very fast, on the order of seconds. And also an added benefit, the calibration is really done pre-production on the analyzer itself. And the last point I kind of want to touch on is process risk. So again, if you hinge an entire process on one unit and it goes down, especially a unit that requires lots of maintenance, that's going to be trouble. However, if you integrate a series of analyzers and one of them happens to go down for whatever reason, well, that doesn't necessarily doom the process, because usually contaminants follow step in step in terms of their concentration. So although there's a small amount of risk, one analyzer going down doesn't necessarily doom everything. So since I'm touching upon a lot of what's going on in the semiconductor world, I think Albert has some comments as well as what's going on in that market.
Thanks, Gary. Yeah, semiconductor is actually very big. There are a lot of things you could be using: gas analysis, you could use inspections, process monitoring, or even just typical just the detection of light or monitoring, etc. These could all be used in that, and also logistics. So today we're just going to touch base with a couple of often seen applications and then how they're used. So maybe two of these are quite often seen. First of all is photo emission, and the second one is thin film thickness. So talking about photo emission, actually it's just to localize the hot spot, which is like a defect we often see in integrated circuits, and causing maybe a shortage on specific either like ESD or probably like other reasons. There are a lot of failures ways, and there are a lot of like ways to identify it. Nowadays in the industry, there's like three typical like major ways to do it, including using a CCD camera for kind of like withstand voltage failure, or in-gas camera for like junction failure and short circuit, and maybe like a mid-infrared camera for short circuits and metallic layers. So nowadays in the industry, actually using in-gas is kind of like a trend because it could identify actually very low light and also not as expensive as like mid-infrared cameras. But like there are a lot of options in the market actually, including indium gallium arsenide, mercury cadmium telluride, and also quantum dot infrared detectors. Often seen actually nowadays, people are using indium gallium arsenide because it's a very mature technology with actually no hazard and high quantum efficiency. So outside of that, actually, near infrared and short infrared could be used in other applications as well in the semiconductor industry, including its capability to see through like silicon. So they use it for wafer inspection and also bonded markings and alignment. So let's jump into thin film measurement. Thin film measurement actually is often seen in not only in semiconductor, but semiconductor uses it as one of the most critical kind of like detection for semiconductor industry due to you need to measure the layer thickness for each process. And to do this, actually, they're just detecting the spectrum of the interference signal, and then you could identify the thickness. The thicker it goes, the longer wavelength it is. And so like actually the accuracy really determines by the sensor's dynamic range and sensitivity. Here's an example of kind of like how the thickness range versus the wavelength goes. So actually for detector side, you have to be able to cover from like 200 nanometers, sometimes even lower wavelength, to like probably 1700, and people maybe nowadays will be beneficial even you use a detector up to 1900 nanometers, depending on what kind of thin film you're measuring. But in this type of situations, we just talked about near infrared, but I want to talk a little bit about UV, because in the lower wavelength, which is around the UV, DUV, EUV region, actually it has a couple of like how like limits when you're detecting the light. Even though you're using a CCD CMOS typical image sensor or a camera, but like you have to worry about two things. First of all, of course, is the damage of the UV light. And also the second thing is about the special window requirement, especially like the damage part for semiconductor industry, or you're using really a long time measurements for automation. You don't want to go in and out, just change it, realign it, and like do a lot of work onto just switching out like sensors. You want a long lifetime with high reliability. But fortunately nowadays, actually with a lot of the detector companies, they are capable to do UV hardness onto the sensor, adding like additional process to increase the lifetime. Also, not only that, but specifically improve the quantum efficiency onto the, we say like the UV region. Instead of in the past, like we have to actually go inside and change the detector all the time. So after finishing about semiconductor, I do want to also, let's talk about in the higher level about electronics. So X-ray actually, we do see also like a higher usages into the industrial automation world, especially like nowadays with the EV batteries, smart components, and PCB like boards, FPCB boards with the smart components, like to identify to identify components or maybe determine the good quality products. X-ray measurement has become more and more popular. So first of all, if we're talking about X-ray detection, usually the first thing comes up to our mind is always the thickness and how small the item is versus energy. But nowadays, like with the improvement of X-ray source capability, actually that's not only the case. Nowadays, with smaller items and like more smart detection range, to detect it, actually the focal point became one of the things that a lot of X-ray manufacturers are focusing right now, and especially nowadays. In the past, it was like millifocus. Now I'm not as microfocus and X-ray sources. Outside of that, to increase the image clear, how clear the image is. Actually, outside of that, there are techniques to also improve on camera side as well. So, for example, time delay integration, accumulating the data, and to increase the signal noise ratio is a great way actually for different types of cameras, no matter you're using X-ray or just typical cameras, actually could improve the signal noise ratio. And we see that more and more used in the X-ray world as well. So after finishing semiconductor, I do want to touch a little bit on the food safety. Recently, we see a lot of like recall, food fraud going on around the world. And we will say that actually food safety could be actually very beneficial from optical detection. Of course, we have to start with the very first, a very typical way to do food safety is in the past, we used like high-speed cameras to do it. So visible imaging, in the past, we've been using a lot of monochromatic, high-speed, low-cost cameras to do food inspection for the shape or maybe some surface imaging. But nowadays, actually, with the improvement of the technology and also like you can like actually take out the filter and actually do like multi-line spectral imaging. In this case, using like multiple lines to identify like specific wavelength, and then create a better, like higher sensitivity, better clear image for the not only the shape and size, but also the color, and you could find out defects on the surface. Other than that, of course, we could talk beyond visible, which is in the short-wave infrared region. And short-wave infrared region has a lot of benefits. First of all, right now, short-wave infrared imaging is like easily used for moisture detection or liquid identification, because it's high sensitivity in the 1100 like to like 1700 region. The second thing about short-wave infrared imaging is actually about like it could identify foreign materials, organic, non-organic. You could see a rock obviously here inside the coffee beans, which is we see it quite often. But also not only that, but also short-wave infrared could actually penetrate some low energy we'll say packaging. So you could do like identify objects under some specific plastics or under like kind of like a filled up beverage package. But people often ask me, so short-wave infrared could be the best way to do penetration? I don't think so, actually, because actually short-wave infrared is very limited to specific materials to penetrate. For nowadays, still, I would say X-ray imaging is still one of the best ways to identify like thicker surfaces, especially like detecting like bones or like identifying like the shape and size, or even checking the filling. X-ray imaging, X-ray is still one of the best ways to identify like internal objects. But there are a lot of X-ray cameras actually in the market, and how do you choose it? This is kind of like a lot of times we get the same question. So we have a list here for you to identify it just based on the density typically, or the object you're detecting, either a line scan camera, dual energy, or TDI, which one would be more beneficial. For example, if you're doing like rubber detection, actually a line scan camera might not be the best option for you, a dual energy, because its capability to detect low and high dynamic range. So it's actually very good for material differentiation, such as rubber or plastic. So talking about imaging, like that's a very key part, of course, about the shape, the surface, but actually how about the footprint, internal like compounds. So I think spectroscopy will be the best way to identify it. And now I'll let our expert here, Gary, talk more about this part.
Thanks so much for that, Albert. So yeah, if we're talking about analytical chemistry, looking at quality of certain nutrients or ingredients, spectroscopy is going to be a very, very powerful tool. And there are a couple of examples to go about that. One could do direct absorption, if you recall the example from before, using a conventional spectrometer. There's very compact options out there, and they're less expensive. But in terms of systems that are looking for higher accuracy, more throughput, one may look to Fourier transform again. And quickly bring up the example again. So near infrared and farther infrared Fourier transform techniques are very similar, but what would be different is the light source providing those starting wavelengths and the detector system, what wavelengths it is sensitive to. But it's still very similar to what we've seen before. There is a light source, something being analyzed in the middle, and some sort of detection module. You can see here from a lot of these, again, usual suspects or simple sugars here found naturally. They have very, very unique footprints or spectra, so they will come up in the analysis if you're looking for them. So quickly want to touch upon what the next generation may be in terms of these analysis. Most people know that you can analyze these types of ingredients with spectral analysis and provide a lot of information at very high accuracy. However, this conventional system of that broadband light source, interferometer system, and then that single point detector is a little bit cumbersome. And kind of the next age is really using broadband lasers to perform these types of analyses. And one of the main benefits here is like these broadband lasers are outputting or have a spectral output as is. You don't need to create that interferogram and then transform it. You're getting a spectral output right from the get-go, and then that goes straight to the detector. Now, what does this all look like? This is a quick example of a polystyrene measurement, and a broadband QCL with a film in the middle, and the detector is able to very closely replicate a Fourier transform spectra. Now, here's the key point. This is completely done in free space. It's able to be done in free space because versus that broadband, versus that, say, filament source and the interferometer system, it's a completely closed system. You have to prepare some sort of sample possibly, but in a free space measurement, it's a lot more mobile, can go in a lot of spaces. So definitely look for quantum cascade technology to find its way more into certain spaces, food being a certain, definitely a possibility. And since we're still talking about food, I definitely want to touch upon Raman spectroscopy. Raman won the Nobel Prize, and for a very good reason. And when you're talking about a very high incident light, in this case, it would be an excitation light, laser. Most of that interaction is going to be what we know as Rayleigh scattering, which is approximately 99% of the scattered light. And what Raman saw was that there's a very, very small amount of Stokes and anti-Stokes scattering that can show up in a Raman shift. And the Raman shifts are extremely unique to the molecule. All the certain bonds pop up in all sorts of ways in the Raman shift. Now, kind of taking an example of that, one can see here, there's a lot of plastics here, but the same will definitely apply to all sorts of nutrients and ingredients and chemicals. The thing about Raman spectroscopy is that the speed's great. One's looking for chemical kinetics or reaction monitoring, very, very popular technique. The sensitivity, as you can tell from the uniqueness of the spectra, very high. It's high specificity. So again, it's going to be popular for plastics, pharmaceuticals, biotech, and yes, can be good for food as well. And in terms of the construction of a system, a lot of conventional detectors and image sensors are used within the visible and the near infrared. However, important to note that since the Stokes scattering is not a whole lot of light to be dealing with, a lot of this, the image sensors, namely utilize back thin sensors for much higher sensitivity. But, you know, of course, there are some trade-offs. So there's a lot of robust detector technology, but these instruments require excitation lasers. Lasers can add cost and complexity. In certain cases, there may be sample prep. There are a lot of Raman spectrometers out there that are kind of point and shoot, but that's when you're looking at what you think to be a pure ingredient most of the time. And sometimes there may be sample prep, especially with certain enhancement techniques. And again, like this system, you're dealing with low light, you have specialized components, so the cost may be up there. But again, a very powerful technique. And taking a quick example of, other than, say, food, there's could also be applied to liquids, namely beer or alcohol quality. Not too long ago, assuring the color of beer was done with what you may think of paint swatches and the naked eye. Not so much anymore. Alcohol as a molecule is not the principles still apply in terms of the analytical spectra. And you can see applying this technique really shows the differences between all sorts of spirits and drinks, and monitoring for certain quality. It would be very, very powerful to deploy a spectroscopic technique. So not everything is completely based on a module, some sort of sample in between light source. A lot of effort has been done to miniaturize all of this. Again, everyone's aiming for these products to be more mobile, more point measurement, especially in the food industry, of course. So a lot of miniaturization has gone on in terms of the spectrometers themselves, but they still have that important grading and detector, which is what you need for a spectrometer to perform. One can see here along the getting close to the near infrared around a 1 micron, you can see spectral characteristics for moisture, glucose, chlorophyll. Still can be a very powerful technique for certain nutrients and ingredients, and of course can be an extremely powerful technique for color on its own. What's a better color sensor than a spectrometer? And so again, there's a myriad of choices out there. There's those very high sensitivity systems, say like multi-channel spectrometers or even Fourier transform systems. So depending on what the application is, you might be closer on that end, or you may be going closer to that more mobile, perhaps lower performance, lower cost. You're looking for information right then and there. So it kind of depends on the setting and the environment. But the point is that today there's more technology choices than ever. So we talked a lot about imaging. Albert touched upon that before, talked a lot about spectroscopy and acquiring spectra, but there's actually a technique where you really combine the two. I'll let Albert take it away.
Thanks, Gary. So yeah, if we talked about imaging, we talked about how strong is spectroscopy, using spectroscopy to identify the content. How about combine these together into one process? And nowadays, there's technique as hyperspectral imaging. Actually, hyperspectral imaging is pretty oftenly used in food industry, especially its capability to identify or the distribution of like an object and also identify the spectrum as well. So it could be used to like kind of fat distribution. It could be used for foreign objects checking, like maybe like especially with similar colors. Actually, hyperspectral imaging is really, really helpful. But there are a lot of ways to do hyperspectral imaging in the field. Nowadays, actually, there are four major ways to do it, including whisk broom, push broom, or you're doing snapshot or spectral scanning. But now in the food industry, actually, I would say like push broom is the most common way, since like it can be worked under a consistent speed. And in most of the food industry, using a conveyor belt to like ship through the process line. So I would say like push broom is most often seen. So here's just an example of how like push broom is set up. So usually you have your object right here. You're using a scanning direction, and at the same time, you're providing your image or your into like a slit, a collimator, and then in this like as a spectrograph, and then onto the camera. In this case, the camera on the Y side, and you could identify like the spectrum on here, and then you're moving this way, so you're collecting multiple hypercubes at the same time. So, like in the real world industry, so here's just an example of how hyperspectral imaging is used. Here's using a hyperspectral imaging shows the estimated Brix value per pixel is, and then you could identify and grade this orange by its sweetness. So talking about, after finishing about like we said, like gas monitoring, and also semiconductor, and also like food industry safety, let's talk a little about logistics and identifying it from an even more way. How about the depth? So we often see like no matter for object selection or transferring like wafer, or maybe like just doing touchless interface, depth measurement is also very often seen. Pretty much nowadays, the market has three major ways to do it. You're using triangulation, time of flight, or FMCW. to identify a depth. There's typical LiDAR capability. We do have a LiDAR session as well that will deeply talk into this, but today I just want to quickly talk about like this is often used in the industrial world as well. Outside of that, there's using like a distance image sensor, using the indirect time of flight measurements to identify the object, not only from a depth perspective, but also on a 2D way. So in this case, you don't need to use kind of like a scanning capability to do that. Instead, you could use a 2D image sensor to directly kind of like observe the object's depth and also the shape. So in the we talked a lot about that, but how about the future of automation? Right now, we're seeing kind of like people using a drone to identify not only the X, Y, Z and lambda together, which means you're collecting the image, you're collecting the depth information, and you're collecting the spectrum information. And we could see this become more and more popular in the future. But not only that, but of course, automation detection technology needs to be improved. In the past, we've been using all these kind of like components or even cameras, modules to identify it. What we see in the future, probably SPAD, photonics integrated circuits, meta-lens, and also on processing side, with deep machine learning will help us actually get more and more into the future, like high sensitivity, smaller form factor, and high processing real-time information. So overall, today, I'll jump into conclusion. In my side, I'd say like I'm really excited for CT optical technology to be used more and more in the future. There are a lot of beneficials already, but to kind of like achieve the real-time 100% inspection and real-time process monitoring, I think still they're not there yet, but we could see a path, and I could see like I could see a lot of innovations coming up. How about you, Gary?
Yeah, absolutely. Like I mentioned in what was going on in the gas analysis world and acquiring spectra from food to semiconductor, a lot of this technology is very young. So we're seeing sensitivity breakthroughs even today. There's so many spaces that the technology can be deployed for real-time analysis. It's ever evolving. I know it's tough, but definitely try to keep up with the updates, keep up those conversations with your vendors and researchers. There's so much that can be done to streamline processes, increase efficiency, reduce emissions, reduce the impact of contaminants, looking at contaminants in food. The list goes on and on. So with how rapidly everything is evolving, innovation absolutely awaits.
So thank you, everybody. And we're open for questions now.
Thank you, Gary and Albert, for that great presentation. We do have a couple questions that have come in. One of which is, what gases are being analyzed in semiconductor applications and why?
I'm sorry, Emily, could you repeat that again?
Yeah, what gases are being analyzed in semiconductor applications and why?
So I mentioned like airborne molecular contaminants before. So that's like a lot of the acidic stuff for HCl, HCF, ammonia. But a lot of these processes also are looking at what's inside the high purity bulk gases that are required to run these processes. So ultra high purity nitrogen, ultra high purity oxygen. There may be levels of carbon dioxide and carbon monoxide in there that you don't want at all. So there are many points in the process where you might want to monitor gas, but other than the airborne molecular contaminants, looking for contaminants inside bulk gases is another key area as well.
Okay, we have another question. Can you elaborate on some of the factors involved in looking into the UV?
Some of the factors involved looking into UV actually, that's pretty broad. Looking into UV, like first of all, of course, it's always the sensitivity of the sensor. The second thing I think we mentioned about it is about the window material. A lot of people have been using, thanks, Ross. So a lot of people have been using like indolus in the past, but nowadays, actually, with the bandpass filter capability, actually you could look into those kind of like, you can look into even with window nowadays. So actually, meanwhile, in the past, actually we do see a lot of like defects on the sensor side because you're using windowless, but using like nowadays with a specific UV bandpass filter, you could identify a high sensitivity onto the high kind of like high throughput through the window. Not only that, but also the sensitivity wise and the lead time. So we have additional, like, for example, like some sensors have additional like process to improve the lifetime by adding to a specific kind of like we say filter in this way. But like, yeah. But anyway, additional process to improve the sensitivity that will actually help the UV sensors to be more sensitive and have longer lifetime. Hope that answers your question.
Great, thank you very much. Another question is there a faster way to identify shape, size, thickness than just a typical camera?
Actually, yeah, there is. There's always the typical camera, like using a full frame is usually, we say, the slowest way to do that. Of course, you could get beneficial if you take up the full resolution into like a smaller resolution. This is always a trade-off between resolution and shape and speed. Outside of that, there are other sensors such as profile sensors that had the center of gravity like integrated onto the sensor that you could like have probably less electronic designs into it to help it kind of like speed up your process, and also adding to a laser into your process if you could design properly accordingly. Other than that, like partial readout capability on your CMOS image sensor will be actually very helpful. In this case, you might check with your specifically about your vendor about does it have it and how do you calculate it. For instance, Hamamatsu, we do have the kind of like a tool up there for you to kind of like calculate what is the partial readout for specific sensors.
Okay, great. Another question we have here is, where is your company on the development on T2SLIR detectors? And are you planning to release models in the market soon?
I'll answer that question. So their Type 2 superlattice is a huge buzz in the market right now because it's trying to break through a lot of the physical barriers that infrared detectors present. However, from Hamamatsu's standpoint, there is a Type 2 superlattice infrared detector on our website right now. You just type in Type 2 superlattice right in the search bar. So that one is available, and we are doing more research and more development into Type 2 superlattice. So definitely look to see more developments in the future.
Great, thank you. Another question is, what challenges does technology face when it comes to integrating with the semiconductor to be a full SoC?
I guess Albert, I'll kind of take on this one when it comes to like I assume a full system on chip. There has been a lot of talk about creating a full, say like a optical system on a chip, and it's a great idea, and I've seen a lot of cool stuff being done. But it kind of goes back to yield and questions of performance and consistency. Another thing is like the type of technology involved and the layering. There's also going to be environmental factors involved. So changing ambient temperature might cause a huge issue. I've also seen perhaps issues of hysteresis. So definitely a great idea, but in terms of yield, operation in the field versus in the lab is another consideration. But definitely a big idea, but there are certainly some growing pains to work through.
Yeah, I could add a little bit more on this part too. Yeah, we've been seeing a lot of actually improvement as on the system on chip situation right now on the development and yield, but still, I don't think the yield nowadays is still very good. We see a lot of more and more actually SoC coming out, but right now, I think we're still facing as like the manufacturing of the fabrication, and also how do we control the process, which actually optical technology comes in a lot as well at the same time, no matter from the manufacturing point or the usage point. Yeah, hope that answers your question.
Great. Thank you, Albert and Gary. Another question here. Acquiring spectra can be time consuming. How can I get the same information faster?
Yeah, that actually just goes down to the sensor side, I would say. So probably I'll steal this from Gary. So on the sensor side, it's actually all about signal noise ratio, sensitivity for the sensor. And when we're talking about optical detection, signal noise ratio is always the toughest thing. So like larger dynamic range, which means you either use a larger pixel size, use lower noise, higher quantum efficiency, and then longer integration time. Actually, in this case, doesn't make sense. So other stuff you have to other factors you have to improve. So it's always about down to pixel size, dynamic range, and the lower noise, which is really about how you design your ROIC and what kind of material you use in the detect.
Okay, great. That's all the questions that I have so far. I'll give people one more moment to see if anything else comes in. But as a reminder, a recording of this session will be sent out via email in a few days, so please look out for the post event email if you're interested in reviewing today's session or sharing it with a colleague. If your questions did not get answered today, which it seems like most of them did, you can, or have a question in the future, you can reach out to me directly at emilyb@spie.org or to go to Hamamatsu or to Hamamatsu at photonics@hamamatsu.com to be connected to a representative. I can also connect you to a representative or point you in the right direction to get connected. And to see a complete list of webinars for our community, you can go to spie.org/online. Hamamatsu has 2 more webinars in their series of 6. One will be held on November 8th and the other one on January 18th. And I encourage you all to register for those as well. So thank you, Gary and Albert and Hamamatsu for putting on this excellent webinar.
Thank you.
Okay. All right, I don't see any more questions, so I'm going to go ahead and sign off. Take care, everyone.
Thank you. Appreciate it.
Bye. Thanks, everyone.
Bye.